In this video, let's take a look at review problems for 22, 23, and 24. First off, we'll prove that n choose r is equal to n choose n minus r, and interpret this in terms of Pascal's triangle. To do this, we'll start with the more complicated right-hand side, n choose n minus r. By definition, that's equal to n factorial over this number, n minus r factorial, times the difference, n minus r factorial. So that's how I figure out a binomial coefficient. N factorial, then this number factorial, then the difference factorial. That is equal to n factorial times n minus r factorial times r factorial. Now, at this point, hopefully it's obvious, but I'll rearrange the terms on the bottom. I have n factorial over r factorial, n minus r factorial, just rewriting which one comes first. And by definition, that's equal to n choose r. N factorial over r factorial, then the difference, n minus r factorial. So that's the proof of this working. Now, in terms of Pascal's triangle, this is the symmetry that we see in Pascal's triangle. So if we write out the first few rows of Pascal's triangle, 5, 10, 5, or 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. In any row, if I start here, these 1s are the same, these 6s are the same, these 15s are the same, and 20 here is by itself in the middle. 1s are the same, 5s are the same, and these two 10s are the same. So this identity gives us the symmetry property of Pascal's triangle. Okay, next we're going to take a look at 423 and prove that n plus 1 choose k is equal to n plus 1 over k choose n choose k minus 1. For this, we will start with the more complicated side, n plus 1 divided by k times n choose k minus 1. So that's this fraction n plus 1 over k times n factorial over k minus 1 factorial times n minus k minus 1 factorial. So that's my definition of this binomial coefficient. N factorial, k minus 1 factorial, then the difference factorial. Okay, n plus 1 times n factorial. N factorial is 1 times 2 times 3 times 4 up to n. Then I multiply an extra n plus 1. So the top two terms multiplied together are actually just n plus 1 factorial. Because these are the numbers 1 through n being multiplied together. If I multiply by n plus 1, the result will be the numbers 1 through n plus 1 being multiplied together. Likewise on the bottom, if I take k times k minus 1 factorial, that's equal to k factorial. That's 1 times 2 times 3 up to k minus 1 times the next number k gives us k factorial. And then this last part is equal to n plus 1 minus k factorial, just distributing the minus sign. And now we see that this matches the definition of n plus 1 choose k. N plus 1 on top, k goes here, and then I subtract the 2, and I get this third term on the bottom. So that's the proof of 423. Finally, for the proof of 424, let's prove that n plus 1 choose k is equal to n choose k minus 1 plus n choose k. All right, to prove this, let's start with the more complicated right-hand side and show that we end up with the left-hand side. Okay, so the first one is n factorial over k minus 1 factorial n minus k minus 1 factorial, like that. The second term is n factorial over k factorial n minus k factorial. Okay, so let's see. Let's simplify this first. We have n factorial k minus 1 factorial. This is n plus 1 minus k factorial. And this next part is n factorial over k factorial times n minus k factorial. Okay, let's now get a common denominator. How will I get a common denominator? Well, let's take a look at these two first. K minus 1 factorial, k factorial. This part here is 1 through k minus 1 being multiplied together. This one is 1, 2, 3 up to k minus 1 times an extra k being multiplied together. So this is bigger than this. This term is k times this. So I will multiply top and bottom of this first fraction by k, so that this becomes k factorial on the next step. Over here, clearly n plus 1 minus k is bigger than n minus k. I have one extra term. And so I will make the bottom here, I will add an extra n plus 1 minus k on the bottom. And to do that, I need an n plus 1 minus k on the top to compensate. And so I have k times n factorial. On the bottom, I have k factorial times n plus 1 minus k factorial. On the bottom, I have k factorial. And then these two combined to give n plus 1 minus k factorial. These are n minus k terms, and then I multiply on the next term. That gives me n plus 1 minus k factorial times n plus 1 minus k times n factorial. Okay, so I now have my common denominator. And I have these two terms on top. I can factor n factorial out, and I get k plus n plus 1 minus k. So that's n factorial times n plus 1 over k factorial n plus 1 minus k factorial. And the top, here are the numbers 1 through n being multiplied together. Then I multiply by the next term, n plus 1. That gives me n plus 1 factorial over k factorial n plus 1 minus k factorial. And by definition, that's equal to n plus 1 choose k. And so the net effect is that by starting with n choose k minus 1 plus n choose k, by working with the factorials, we end up with n plus 1 choose k. Now, what does this mean in terms of Pascal's triangle? In terms of Pascal's triangle, well, this is basically how we figure out Pascal's triangle quickly when you first saw this, probably in high school. 1's on the side. Then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1's on the side. And so what this shows is that these binomial coefficients actually match what happens when you use to construct Pascal's triangle in the first place. So this right here is let's call that the nth row k minus 1 column. The next entry would be the nth row kth column. Then when I add them up, the column number here is going to match the column number here. So it's the next row, the n plus first row, but it matches the kth column because these two numbers are in the same column of Pascal's triangle. And so that shows that we have this binomial sum, both in terms of factorials and also how that relates to the construction of Pascal's triangle.